To close this section, let's look at some of the properties of logical operators, both to understand the properties themselves and to explore truth tables a little bit more. First, Boolean operators are commutative. What that means is it doesn't matter what order they come in. If the result of A and B is true, then the result of B and A will also be true. That makes some logical sense in terms of our examples from before. If it's true that grapes are both in stock and on our list, then it's also true that grapes are both on our list and in stock. It sounds almost silly to have to say. Which one we say first is never going to change the value of the overall answer, at least not when we're only using one operator. The commutative property also applies whenever we have multiple of the same operator. So A and B and C would be the same as C and B and A. And the same thing applies for OR. A or B or C is the same as C or B or A. However, if we start mixing our ands and our ors, then this isn't guaranteed to be the case. So that's why it's important to use parentheses to tell the computer in what order to read more complex logical statements. More interestingly, logical expressions or logical operators are also distributive. What that means is that A and B or C is the same as A and B or A and C. We can distribute the A and to the B and to the C itself, resulting in A and B or A and C. This is kind of like math, actually. If we had something like 3 times x minus 2, then we can distribute the 3 to the x and the 3 to the 2. So the point of these two tables is to show that these two expressions are the same. We can trace through one real quick just to see how it works. Take row 4, for example, where A is true, B is false, and C is false. For A and B or C, A is true, but B is false and C is false. Because both B and C are false, it's false that B or C is true, and so it's false that A and B or C is true, and so we have a false. For our second expression, A and B or A and C, A is still true, but B and C are both false. That means A and B is false, and that A and C is false. And because both those are false, A and B or A and C is also false, and so we still have a false down here. These same principles apply for any combination of and or. A and B and C would have the same result as A and B and A and C. A or B and C would have the same result as A or B and A or C, and so on. And finally, there's an interesting application of these operators called De Morgan's law. It allows us to convert ands into ors or ors into ands. It looks kind of like the distributive property, but it's actually a bit different. It says that the result of not A and B is the same as not A or not B. That sounds a little cryptic, but if we think about it in real terms, it makes a little bit more sense. So with our grapes example, we could rewrite this as A is in stock and B is on list. And our statement is not in stock and on list. If in stock is true, but on list is false, then in stock and on list is true, and then the not of that statement is false because it just alters that value. What this says in real terms is that if it's true that we didn't buy our grapes, then it was false that they were in stock and on our list. If they were both in stock and on our list, then it would have been true that we bought them, and it would have been false that we did not buy them. But what that means is that for us to have not bought them, they must have either been not in stock or not on our list. One of those two things must be true, that they're not in stock or they're not on our list, or else we would have bought them. So this version of De Morgan's law takes an and makes it into a pair of nots with an or. But De Morgan's law can apply the other way as well, taking an or and making it into an and. Not A or B is the same as not A and not B. To put that in terms of our grapes example again, if A is on list and B is on sale, then not on list or on sale would suggest that if it's true that we didn't buy grapes, then they must both be not on our list and not on sale. If either of these were true, then the or would be true and the not would be false. And that again matches our logical understanding of that problem. If we didn't buy them, then they must have not been on our list and not been on sale. Because if either of those were true, we would have bought them.